So question 1, find the minimum value of n bigger than 1 such that 3 to the n is congruent to 1 mod 11. So who came up with an answer for this that you remember because you already turned it in? So what did you get for an answer?
5.
5? Cool. I like the consensus. That's good. So how did you find that?
Brute force.
Brute force.
Yeah.
Use the
Yeah.
table.
Use what?
I used the table.
Okay.
Table and gradually
And eventually found one that was congruent to 1. So I really didn't intend anything here other than brute force, right? And if you invoke Fermat's little theorem, what does that tell us about anything related to this?
11, 3 to the 11 minus 1 is congruent to something mod 11.
Yeah, so Fermat's little theorem tells us in general that a to the p minus 1 is congruent to 1 modulo p. And so here we're looking at powers of 3. And if we look modulo 11, that tells us 3 to the 10th is congruent to 1 modulo 11. So we know that's the biggest our number might be, is 10. We know if we get up to 10, 3 to the 10th will be congruent to 1. But we're looking for the smallest positive integer, so you got to start with 3 to the first, second, third, work your way up. And when you hit 5, it turns out to be also congruent to 1. So this doesn't tell us the smallest, it tells us a number which satisfies that condition. But it's just plug in and see what the first n is that satisfies that. All right, so what are these congruent to modulo 3? What's modulo 7? What's 37 mod 7? It's not 3. What is it? It's 2, right? 7 times 5 is 35. So 37 is congruent to 2. This is all mod 7. Right? Or how much do you subtract from 37 to get a multiple of 7? Or what's the remainder when you divide 37 by 7? So what about 66? Right, because 7 times 9 is 63, so that's 3 more than a multiple. What about negative 17?
That's negative 4. It's positive 3.
Negative 4, so it's positive 3.
Yeah, so positive 3, positive 3. So negative 7, one way to do these is to start subtracting 7 until you get down to something small. 37 takes you down to 30, takes you down to 23, takes you down to 16, takes you down to 9, takes you down to 2. So for the negatives, you can go in the other direction, just keep adding. Negative 17, add 7, you get negative 10, add 7, you get negative 3, add 7, you get positive 4. And that's the magic number between 0 and 6. So you can do that with all of these, right? Negative 67, I don't know what that turned out to be, but add 63, it'll be negative 4. I think that turns out to be 3, right? Okay. And how about 3? 3 is congruent to 3. How about negative 3? So negative 3 is congruent to 4. All right, so 3 was one of these questions that I wanted you to just kind of like think about and see if you could get anywhere with this. And it's not the ideal form of this question, but there's some things you can get to with this. So suppose A, B, C, D are integers and D is bigger than 1. Is it always possible that this function generates a prime number? And your gut should probably tell you no. But why is it not possible? And the hint here is consider what happens when x equals D. So we've got ax cubed plus bx squared plus cx plus d. That's f of x. And we want to know if this can always be a prime for whatever value we plug into x. Yeah?
If x equals d, then the solution to f of d will always be divisible by an integer d.
There you go.
And prime cannot be divisible by any integer other than itself and 1.
Exactly. So if we evaluate f of d just using this formula, it turns out to be this long thing, which is just d multiplied by ad squared plus bd plus c plus 1. And this is an integer, presumably bigger than 1. There could be a pathological case here. And this is an integer bigger than 1, and so this expression is the product of two integers bigger than 1, neither of which is the expression itself, so that makes it composite. All right, Euclidean algorithm. So any issues with this? You did a bunch of these on the board last week. A lot of them equaled 1. Like 100 and 101, I'm guessing. And 1 in 5. Were any of them not equal to 1? Okay. Was that E? Okay. Yeah. All right. So let's talk about number 5. And we haven't really, I think I mentioned something about this once, but we haven't worked through this, and I want to work through some of these on the board. But did anybody make any headway on question 5? What did you do?
So if it's 4 consecutive integers, if you let, so if you just take a number n, then so it's, you need essentially n times n plus 1 times n plus 2 times n plus 3.
Okay.
And then to prove that number is divisible by 6, it would have to be divisible by 2 and also divisible by 3. And if n is odd, then n plus 1 is even.
Okay.
And if n is even, then n plus 1 is odd. So you would.
No,
it's
that's
always
good.
going to be an even number.
Actually, we do not care the even or odd. We just use the mode to calculate the n mode 3, follow the sequence 0, 1, 2, 0. So we get a conclusion that there exists 2 numbers could be divisible by 3.
Okay, so there's at least 2 approaches here. The first is the argument that you're doing, which is to basically look at this and show that you said something interesting. If it's divisible by 6, we can just show it's divisible by 2 and 3. That's a pretty powerful statement, actually, that is valid, but you have to do some work to show that if something's divisible by 6, it's actually divisible by 2 and 3. But that will get you there, and then you were trying to show that one of these is even, so that product's divisible by 2. And then you can do some work to show that
If n mod 2 is 1, if n mod 3 is 1, then n plus 2 would be the mod equals 0. So
right.
working through that, a number would be divisible by 3.
Okay, and that starts to lead into what you said, and also goes in with this. Did I put a hint? Nope, I didn't. So the nice thing about working Mod 6 is that we don't have an infinite number of things to consider anymore. We only have 6 things to consider, right? So this says, using modular arithmetic, show that the product is divisible by 6. Divisible by 6, think congruent to 0 modulo 6, okay? 6 is sort of the most natural modulo to work in if we're looking at divisibility by 6. We could also do 2 and 3. But the first order, think congruent to 0 mod 6. So let's look at this product and see what we can say about this modulo 6. Well, the problem is we don't know what n is. Is it 1? Is it negative 12? Is it 10,518 and 7, right? But since we're working modulo 6, we don't care if n is equal to 7 or 1,000,003, right? We only care what is n congruent to modulo 6. Because we know that if we're working mod 6, we can do arithmetic. And the answer we get at the end will be the same as doing arithmetic on the original numbers and then reducing modulo 6. So what can n possibly be congruent to mod 6? Yeah, 0, 1, 2, 3, 4, or 5. So there's 6 cases. And these problems are always sort of like hidden attempts to get you to say, let's just look at a small finite set of cases. So, well, this is what n is. Let's write down what n plus 1, n plus 2, and n plus 3 are. So if n is congruent to 0, we know what n plus 1 is congruent to. It's got to be congruent to 1, right? That's what modular arithmetic does. And n plus 2 has got to be congruent to 2, n plus 3 is congruent to 3. If n is 1, this is 2, 3, 4. If n is 2, this is 3, 4, 5. If n is 3, n plus 1 is 4, n plus 2 is 5. What is n plus 3 congruent to? Right? It's 6, which we also know is congruent to 0. So now we have a much smaller problem. And for each of these cases, we can write down what's the product of these 4 congruences. And this is 0 times 1 times 2 times 3. This is 2 times 3 is 6, times 4 is 24. That's congruent to 0. This is 2 times 3 is 6. That's congruent to 0, times 4 times 5. Here we've got a 0 over here. There's a 0. There's a 0. And so in every case, you've shown the product of these 4 numbers is congruent to 0. Mod 6, so it's divisible by 6. And that's something we can throw at a lot of these problems, right? And it's really just saying if we could look at that first equation for every possible value of n and show that it's always a multiple of 6, we'd be done. But there's an infinite number of n's we have to consider. If we jump into mod 6, there's only 6 n's to consider, basically. So I'll have you work out another one of these on the board, and I want to have you work out some more even odd number proofs. Show n squared is even, if n is even kind of stuff. But before that, let me go ahead and talk through the midterm list of topics, and then we'll spend the rest of the time working on some of these proofs on the board. So any questions on that homework, first of all? Should I click on midterm or on topics? I'll do topics. All right, so I posted this on Canvas last night. And obviously, all of this is not going to be on your test. Your test has 7 questions on it. So, and some of them are fairly short. You know, calculate this set operation, this summation, things like that. Couple of proofs, couple of things working with propositions and logical equivalence and things like that. So, 7 questions total. All right, so let's just go through this, and if you have questions as we go through it about this or other things, right, just chime in. So first thing was basically set theory, so notion of a set, right? Sets don't contain duplicates, they're unique collections, they are unordered. Set operations, union and intersection are the 2 big ones. We can subtract B from A, that's the complement of B and A, it's also A backslash B. And we're basically starting with everything in A and then throwing out anything that's in B. And if we complement a set in the universe, right, so B with a little uppercase C, is what the book uses, or B with a bar on top, right? That's basically the whole universe with anything that's in B thrown away. So it's the stuff that's not in B. It's just sort of the usual complement. The universe is the biggest set. It contains every possible thing in whatever space we're considering. And the empty set is the smallest possible set, and it contains nothing. So if we're working over the integers, the universe is the set of all integers. The empty set is the set containing nothing. A subset is just a collection of elements from some larger set. So here's our original set. If we take some collection of elements from there, we can create a subset. And the subset could be the original set. The subset could be completely empty, or it could be something in between. So a proper subset is something that's a subset but not the original set. So the set of all integers is technically a subset of the set of all integers. But a proper subset might be the set of positive integers, or the set of integers with the letter E in the name when you write out the name in English. So those are subsets. The power set of a set is the collection of all subsets of that set. Right? So it's a set itself, but the members of that are all the subsets of your original set. And we did a bunch of examples of that. Membership, so we have this epsilon symbol to say this thing is a member of that set. And it just means it's one of the things found in the set. We introduced set builder notation, so the curly bracket thing reads the set of all x such that x is bigger than 9. So it's just a way to define sets. Cartesian products, so if you have two sets A and B, we can take all the ordered tuples where we take something from A and something from B and we pair them together, and that becomes an element in the product. So the Cartesian product is a set of all those pairings that we can create by taking a first element from A and a second from B. Venn diagrams, so we looked at these pictures of set operations. So here's the universe. And here's a set A. And here's a set B. And here's a set C. And if we look at this part where A and B overlap, right, so that's the intersection of A and B. And if we look at this place where all three overlap, that's like A intersect B intersect C. And if we look at this set, which is everything in A plus everything in B, that's a union, and so on. If we look at this set, which is everything in A, but with the stuff that's also in B removed, that's A take away B. And so you can draw pictures of sets and set operations like that. Summations and double summations. I definitely want you to know how to do summations and double summations. So sum from I equals 5 to 8 of 2 times I squared. As an arbitrary example. This is a shorthand. It says set I equal to 5, write down the value of this expression. 2 times 5 squared. Set I equal to 6, write down this expression. 2 times 6 squared. Set I equal to 7, 2 times 7 squared. Set I equal to 8, 2 times 8 squared. That's as far as we go because the upper limit is 8, and then just add all of those expressions together. So that's a direct expression of what that summation symbol means in this case. And again, it's just a for loop. Right? This is for I equals 5 to 8. Sum equals 0. Sum equals sum plus 2 times I squared. Right, so that's how we write it in code. Really weird language. So everyone okay with that? So a double summation, we can do the same thing. This is one of these moments where thinking less is beneficial. I'll keep it simple, I'll just do ij. So sum from I equals 5 to 7 of the sum from j equals 2 to 6 of I times j. And if we break this into two pieces, we can first say, what does this summation mean? It means set j equal to 2, write down this expression. This is I times 2. Set j equal to 3. Set j equal to 4. 5, and 6, add them all together. That's what this summation is equal to. And so now we can rewrite our problem, sum from I equals 5 to 7 of, and let me write this in a normal order, 2i plus 3i plus 4i plus 5i plus 6i. Which, if you've done algebra, we could save ourselves some ink by saying, well, this is 2, 5, 9, 14, 20i. This is just 20i. And now I can say set I equal to 5. This is 20 times 5. I equal to 6. I equals 7. Add those together. And that's what the double sum is.
So double sum is basically nested summations?
Exactly. That's exactly what it is. And so if we did this in code, set a running sum equal to 0 for I equals 5 to 7, for j equals 2 to 6, sum equals sum plus I times j. There's the code equivalent. And basically what we discovered up there is that each time we do this, we will get the value of 20 times I added to our sum. But we don't need to know that if we're writing code, because the computer does everything for us.
So we have questions that you'll make this translate into code? Or-
No, I won't have you translate into code. That's just another way to think about it. But I may ask you to do something like this. All right, so summations, double summations, functions. So let's take a vote. Have I talked about injective, surjective, bijective functions in here? Okay, so take that off the list. I won't ask you about those. Well, we'll probably talk about them another time because they're good to know. So don't worry about types of functions. Membership tables. So this was a way that we could explore various identities and properties of set operations by making something like a truth table, but where the columns corresponded to whether an element belonged to a set or didn't belong to a set. So here's a set A, here's a set B, A intersect B. So we can say, does a particular element belong to set A? And I can write a 0 if it does not. I can write a 1 if it does. And so for any element in the universe, there's exactly 4 possibilities. It belongs to neither set. It belongs to both sets. It belongs to only B, or it belongs to only A. Those are the only possibilities. And so if for each of those possibilities I can describe whether your element belongs to the intersection, I've got a complete description of what this intersection is. And the way this looks is if your element does not belong to A or B, it's not a part of the intersection. If it's not in A, it's missing from the intersection. If it's not in B, it's missing. But if it belongs to both A and B, it is in the intersection. So there's a membership table for how an intersection works. And we can make another column for how a union works. And if an element does not belong to A or B, it's not going to be in the union. But if it's in either B or A or both, it will be in the union. And so there's a membership table for union. And from 250, you recognize this first column is just the truth table for an and, the second one is just the truth table for an or. So there's connections between these set operations and the logical operations that we've been using in other courses. So just like we can prove various identities about Boolean expressions, we can prove various identities about logical expressions. For example, we can prove that very easily with membership tables. That's De Morgan's theorem for sets. And we do it by enumerating all the possible cases, and for each one showing that these have the same value. So theorems about sets, well that's the last thing. They're proving identities via membership tables. And then there's theorems about sets. So we have various theorems, and there are things like commutivity. So union and intersection, the order doesn't matter. Associativity. Which says we can group these in whatever groupings we want and the answer doesn't change. Distribution. Right, which says we take that intersection, we can apply it to each of the elements. And De Morgan's theorem, and so on and so forth. Along with some of the other things like A union, the empty set is A intersect the empty set is the empty set. A union with the universe is the universe, A intersect with the universe is A, and a whole bunch of things like that. And we can use these to prove theorems about sets in the same way that we use the Boolean equivalence to prove theorems about Boolean expressions. Right, so you've done this before. It's just a different domain, but it's basically a parallel domain. So that was pretty much everything from set theory that I think we talked about. The next unit was logic. So we talked about propositions. So what's a proposition? Declarative statement that has a truth value. Okay, if you do that, you can't go wrong. So writing propositions, right, let P be the proposition, colon, today is Monday, or whatever, right? But don't let P be the proposition x plus 1, because x plus 1 is not a declarative statement, right? Let P be the proposition that y equals x plus 1. Y equals x plus 1 is a declarative statement. Okay, so always come back to that definition. Make sure when you're writing propositions, they're declarations. So mostly we derive new propositions from old, and this looks a lot like set theory. So we can take propositions P and Q, and we can take their conjunction, which means and. We can take their disjunction, which means or. We can take the negation, which means not. We can combine these. So we can say take the conjunction of P with Q and then negate the result. And if P and Q are propositions, each of these will be a proposition. Today is Monday, today is Tuesday. Today is not Monday. Today is Monday and today is Tuesday. Today is Monday or today is Tuesday. It's not true that today is Monday and today is Tuesday. Right? Each of those is a declaration. So you can put these things together. If P, then Q. So this is an implication or a conditional. If today is Monday, then today is Tuesday. That's a proposition. Here's a more reasonable sounding proposition. If today is Monday, then today is not Tuesday. Well, that's a nice true proposition, right? Because you know if it's Monday, it's not Tuesday. if today is not Monday, then today is Tuesday. That's a proposition. It doesn't turn out to be true, because it could be Wednesday. All right? So this is related to this, right? It's the inverse, because we're negating the two sides of this, and the inverse is not logically the same as the original. We could flip these around. P implies Q. We can flip that around. Q implies P. That's the converse. We can also change this into not Q implies not P. And that's the contrapositive. So different ways to create new implications from old. So converse, inverse, contrapositive are the main three. Contrapositive is logically equivalent to the original proposition. Converse and inverse are not necessarily. P double arrow Q is an if and only if, right? So P arrow Q we can read as if P then Q. Okay, we don't normally do this, but we could also write a backwards arrow, and we would read this if Q then P, but the arrows usually go to the right. But then if we do a double arrow, that's a shorthand for a conjunction of the following. If P then Q, and if Q then P. And so that turns out to be P if and only if Q. They have to both be true or both be false. So that's the double arrow. So we can write truth tables for propositions. And they look like truth tables for Boolean functions. They look like membership tables for set theory. There's a lot of redundancy in this course. When we're done, you're going to be like, wow, we only did a week worth of material. So we can write truth tables for propositions, right? And that's one way to analyze things like, is this proposition equivalent to that proposition? Propositional equivalence, right, means that these two propositions always have the same truth value. They're effectively the same truth values. They might be very different propositions. Right, P might be the proposition that today is Monday. Q might be the proposition that tomorrow is Tuesday. Those always have the same truth value, right? Even though they're different statements. And we can prove propositional equivalence using truth tables, just like we can prove set identities or Boolean identities using truth tables. And we also have a set of identities that we can use to prove propositional equivalence. So again, commutativity, P and Q is the same as Q and P. And other things. So page 58 and 59 in your text. Right, 58, we have all these identities for propositions. So P or 0 is the same as P. P or P is the same as P. P and P is the same as P. P ANDed with P or Q is the same as Q. De Morgan's laws, of course. The negation of P is P, and so on. And so we can take some of those and throw them at other statements and show that things are the same. Or we can use truth tables. Quantifiers. So for all x, P of x, where P is a proposition that presumably depends on x somehow, this means for all x, P of x is true. And P of x could be the proposition, today is Tuesday. And this would say for all x, today is Tuesday, and it doesn't really depend on x. So there's nothing wrong with that, but usually this is something that depends on x. So for all x, P of x might be the proposition x squared is bigger than x. Right, that's a declarative statement. And so for all x, P of x, this is a statement that for all x, x squared is bigger than x. And if x could take on the value 1, this is not true. 1 squared is not bigger than 1. So it's not true that for all x, P of x, assuming we're working over the set of all integers. So typically we would say for all x contained in Z, for example. And so for all x, P of x is false, but there exists an x such that p of x. That's definitely true, because if x is equal to 2, 2 squared is 4, that's bigger than 2. So this says there exists at least one. This says for every possible x, this is true. And with an exclamation mark, this means there exists exactly one x. There exists a unique x. We haven't done much with that. So those are quantifiers, and quantifiers can be nested. For all x, there exists a y such that some proposition of x and y. And again, throw in parentheses. Because this is a proposition. It's a proposition that depends on x. Right? And it says there exists at least one y such that p of xy is true. It may depend on the value of x, but that's okay. This is just a proposition that depends on x, and this is just for all x, whatever that proposition is. And the same if you nest in the other order. So quantifiers, rules of inference. So this is leading us into proof. So again, page 59 of the text, we've got all our rules of inference. Detachment or direct reasoning, indirect reasoning, disjunctive addition, conjunctive simplification, etc., right? And these are ways that we can say, okay, if we have this thing on the left, that implies this thing on the right. Okay, they're not equivalent. If P is true, then we know that P or Q is true, right? But P is not the same proposition as P or Q. P could be today is Monday, Q could be I just won the lottery, right? So if today is Monday, then it's true that today is Monday or I won the lottery, right? But these are different statements, because if I won the lottery, this would be true even though P might be false. I didn't win. I'm so sad. I had great plans. But the thing on the left implies the thing on the right. Or in this case, the thing on the left is equivalent to the thing on the right. Okay, so these are ways that we can do proofs, which is where this is heading. So rules of inference, proving an argument is valid, P1, P2, P3 implies Q, and so on. So this is stuff like the following. Given P1, P2, and P3, can we prove Q? So this is where you want to be very formal, and you want to write down a set of steps. You're allowed to assume, in this case, P1, P2, and P3. And then we can assume, since those are true, anything that follows from the truth of those is also true. So we might say, you know, step 1, P1, and that's a premise. And step 2, P2, and that's a premise. And then we might say step 3, P1 and P2, and that's a definition of conjunction, right? But if these are interesting expressions, we can start to say the contrapositive of P2 is also true, and we might be able to use a chain rule and so on and so forth. So we're going to play with that some more today. But that's basically how we turn these things into proofs. So fallacies are the things that are not in here. Okay? Detachment, direct reasoning. Looks like this. So we're told if P then Q, and we're told P. Or we're told P is true, and if P is true then Q is true, so we can conclude Q is true. Right? That's detachment, that's direct reasoning. Okay, this is indirect reasoning. If P is true, then Q is true. Q is not true. There's no way P can be true. Because if P is true, Q's got to be true, and Q's not true. So this is enough to conclude P is false. Okay, that's indirect reasoning. If I win the lottery, I'm not here right now. But I'm here right now, so I didn't win the lottery. I would have come in anyway. Hand out money. So those are logically correct, right? There's fallacies that go along with these. So one fallacy, if P then Q, not Q, Q, therefore P. So if P is true, then Q is true. Q is true, therefore P must be true. That's not logical. Right. So do you remember what that fallacy is called?
Affirming the conclusion?
Fallacy of affirming the conclusion, because we're saying the conclusion is true. So that's a fallacy. And those are pretty easy to come up with. If I win the lottery, I'll wear a suit today. I'm wearing a suit. Must have won the lottery. Okay, you get the idea. The other fallacy is denying the hypothesis. So if P, then Q, not P, therefore not Q. That's a fallacy. If it's Friday, I'm going to eat my lunch after this class. It's not Friday, I'm not going to eat my lunch. Doesn't follow. All right, so this is fallacy of denying the hypothesis. So make sure you know these, right? This is detachment. Or direct reasoning. And this is indirect reasoning. So these are valid. These are fallacies. All right, and then proofs. Two main methods of proof, direct and indirect. Indirect is a proof by contradiction, but it's also a proof of the contrapositive. Right, so we're assuming the negation of the thing we're trying to show, and we're arguing to a contradiction. And know about even and odd numbers. We're going to work on those at the board in a moment also, because you'll have a proof about even and odd numbers. So again, sort of working systematically and describing why each step follows from things you've already shown are true. And then the last thing we worked on was number theory, and you just did a homework set on this. So basically the notion of prime numbers, numbers that are only divisible by themselves in one, modular arithmetic, so we did that on the board, and I think everybody got that nailed, with modular exponentiation, which is just using modular arithmetic to simplify your life. Fermat's little theorem we just talked about. Greatest common divisor. In Euclid's algorithm we just went through some examples. And then proving facts about integers, like the sum of any three consecutive integers is divisible by 3 using modular arithmetic. Again, as soon as you see that, divisible by 3, think, what if I work mod 3? And if you work mod 3, you don't have to work with any 3 consecutive integers, because you only have 3 integers to deal with, 0, 1, and 2. Any integer that you pick is congruent to either 0, 1, or 2. You've got 3 cases, right? And for each of those 3 cases, you can write down an expression for the sum of those 3 consecutive integers and show that it's divisible by 3. So that's the hit list for the midterm. Like I say, 7 questions, 50 minutes. And my plan is to give people about 5 minutes to come in late or ask questions. Don't ever ask questions before a test. It never helps. It just gets confusing. And don't listen to other people talk about it. Just like, it's always, for me, it was always bad. So I'll give people about 5 minutes to come in across campus. So we'll start at about 12:35. We'll take 50 minutes. And then I'll give you like a 5-minute break to stretch your brains. And then I'd like to go through the exam in class at that point, just while it's fresh in your brains, and talk about any questions on it and such. And so probably no new material on Friday. And then Monday we'll kick in with induction and get back to that full force. And I posted a playlist of 6 videos on induction. If you want to look at those sometime between now and Monday, that can be helpful. But we'll be talking about induction probably most, if not all, of next week. All right, so questions about any of this? Okay, I'm going to bring up lights slowly. And let's go to the board in groups and start with this first question of prove that the sum of any 3 consecutive integers is divisible by 3 using modular arithmetic.
The multiplication to just plus?
Yeah.
So we're going to have n plus 1.
And part of the goal in this question is how you do it. Okay, you can probably see pretty quickly that the result is true, but the goal is to be able to demonstrate it clearly.
So
Then we do it. So then we do the.
So think about how to write
mod
it.
3. So there's 3 possible states for any number, mod 3.
I'm so sorry.
I would perspective like congruent. Because we're not saying that it can only be 0, 1, 6. We're saying congruent to 0, 1, 6. Wait, think of that. If n is congruent to 0, then n plus 1 must be congruent.
So you mod 3,
Oh.
you know it's always going to be
And then we can take the addition. That's going to be 2. The addition?
Oh, I think multiplication from earlier.
Yeah. So all of those in mod 3 would be equivalent to 0. So we can say any 3 consecutive numbers would be divisible by 3.
Is that if you add was the congruency of the 3 to 3 consecutive words?
Well, I skipped a few steps.
So we can say
I just like, it's mod 3.
No, a different one.
so if we know n is congruent to 0, n plus 1 is congruent to 1, and n plus 2 is congruent to 2, all of those added to each other is going to be congruent, which is congruent to 0. So it is
Product is going to be divisible by 3.
Well, it's actually going to be divisible.
Yeah.
Well, all of them are divisible by 12. I'm not sure about the money.
Depends on how. Because the first set can be 0, 1, 2, 3.
Well, the first set will be divisible by 12. Like, once you go high enough.
Did you have parentheses?
Because you'll need 3 sets of 2. Yeah. You'll have 2 sets
Well,
of
it's
2.
good. It's not better. It looks nicer. It still ends up the same. Or wait, no.
I mean, if you were to algebra that out, it would be 3n plus 3. You could just say those is gonna be a factor of 3. It's always divisible.
Yeah, you could do this out. Yeah, actually that's a pretty good way to find out. Because 3 and multiplying the number by 3,
Yeah, that's
you know,
what I
it's
see.
I didn't say I didn't just adding those 3 to the log, that's still going to
Would you say it's
Yeah.
congruent to 0?
It's also, this is still a set equal to 0.
3 mod.
It's the same thing.
Be really clear that n is congruent to 0, 1, or 2. It's supposed to equal to.
So who's the
No, I'm taking 2, 4.
Yeah.
That's
I'm
what we're
surprised.
setting up.
And
School and some the lights are off and then just stepping on the front.
yeah.
At least that's what I go to I plus 2.
So back up. Tell me what p of x means.
P of x is the function. That's the summation.
Okay.
We're going to P of 1, P of 0,
Manage it on the
I of 0.
Just make a nice or
Okay.
Go to the end of the point and let's go.
And replace the summation with P. So you have 0 to 2.
Okay, so like this.
Yes.
Okay, so that's the sum of the kind we're starting at.
Fire.
Yes. Okay, got it.
I don't want to consider the proofs to be ignorant. Yeah, we'll be doing it kind of somewhat pretty weird.
it's congruent
is a factor of the equation.
Right. So that gives you your answer right there.
So
But if you have to do it with modular, then you would need this case.
Something like the definition of divisibility. Like the definition of something like that.
So that's just congruent
There
to
was
1.
the K, that's an integer. N is odd, it's 2k plus, n is equal to 2k plus 1, k is an integer.
I don't think I have that.
N is even if there, n is equal to 2k and k is an integer.
All right. Good here. Good. You got this? 0, 1, 2, 1, 2, adds up to 3, which is 0 modular. Good, perfect. All right, so using modular arithmetic, show me that an even number times an odd number is always even.
looking at the exact same thing. Do you want to write this one out?
Even number, what was it? An even number times an odd number.
Times an odd number.
Oh, an even number times an odd number is always one.
So even times odd is even.
Even times odd is even. No, it's even. Okay.
Even times an odd is going to be an
Oh, yeah,
even.
yeah, yeah.
But you gotta do this using modular arithmetic.
5 times 7 is like even an odd number.
I would probably start out with the definition of even and odd.
But don't we say like, well, oh no, they're not consecutive, so we can't use the
When we say like n1 is our even number, n2 is our odd, and we know n1 is equal to some integer k, 2 times some integer k plus 1. That would be our n2 for our odd, and our n1 would be.
So what modulo do we want to work in? Because you have to do this using modular arithmetic. Modulo 2, right? That's going to work really nicely with evens and odds.
N1 would have to be equal to some integer k, 1 times 2. K1 times 2, or you just did k. And then you know n2 is going to be 2 to 0.
Prove that find the even number and odd number you get.
So one issue I have with that, I didn't say that the denominator was even number plus 1.
It's just the
But it's a small change on that.
So instead do
The definition of option.
these two. That's why I say n2 is equal to k1 plus 1.
We know it's always going to be an even number, then whatever the result is, it's going to be 0, not 2, right? So then 0 is 1 for you, 3.
Definition of even
The value of n is value into
but then you'd want to use
expressions.
k.
Let n equal even like k equal odd. Okay,
Yeah, for some reason I still think really doing consecutive. Then we'll have to change.
So the definition of an odd number.
2k plus 1. And k is some integer.
So we're saying that k times 2k times 2k plus 1 will always be even. So we can just kind of do algebra once we get the evaluations in.
It also needs to be k1 because it's not necessarily the same number.
We need to prove that fits the definition of an even.
Is equal to 2k, I'd say like 2k3.
If n is even,
Or 2k2.
We can just algebra.
And just like k never feels.
What do you got?
n is an even number, k is an
Probably-
odd number.
Okay.
I would probably
Two,
do like
0 and 1 with both plus the
distribute it.
Alright, so show me that odd plus odd is even.
K1 plus 2k0.
I think I actually just like multiply just directly and see what it is. So just like do the full FOIL. Don't try to solve it.
Okay.
So we can do it this way.
So 0, 2k1.
Yeah.
Well, it'd be 4K. 4K.
You've got enough there to generalize.
And then you could
So
divide by 2.
Where did you get the equals? Or, I guess. So we need to manipulate the left side to look like the right side.
Any even number times any odd.
We want it to look like. Well, we know that.
So that's the general.
Well, actually, wait. So this is some integer, right? That's some integer right there. And you're
Well, let's just take 2 away from here. Let's just.
yeah, go ahead and take out the 2.
I meant just grouping ones. Like move a 2 out in front of it. So not dividing everything up. Just like factor out 2.
Oh yeah.
If you're working with odd even, mod 2 is going to work best. Because evens are divisible by 2, so they're
If
So we
prove
can say-
this is an integer, then we know 2 times this integer is going to equal to an even integer.
Yeah. So we can say that K2 is equal to all of that. Yeah.
Yeah, K2 is equal to that, and 2 times K2 is
So yeah, we're going to change these to be K0, K1. It's like saying that. And I think that's.
And then you can say, so then 2, K, 2, and the definition of an integer is.
Oh, see, that's uppercase.
We don't know if that is.
You have an odd number.
This is our n.
Some other odd number, what's that?
The thing with the mod, giving numbers any two odd numbers consists of both the zeros.
But I think this is fine.
Yeah, I understand, but yeah, that's showing that like really like everything you want.
I'm pretty sure, but just looking at like the earlier proofs, like for example, we were asked to prove if n is odd that n squared is odd, and it's pretty much exactly like this. We just algebra it out, and then we say like we have 2 times 2k squared plus 2k plus 1. Then we say 2k squared plus 2k is going to be an integer. Let's call it j. And now n squared fits the definition of odd.
So we're
That is, you can have an odd,
If this was a formal proof, then we would say in steps that n1 by the definition of even, n2 by the definition of odd, then this would be algebra. And we would have equal, and then eventually we would say, this is an integer, so there exists a k2 such that it fits this one. Yeah, we did this stuff like week 2
And then basically for my note page, I can get the note page on my notes, I've just been going through this. Basically just compressing all my notes.
I try to write when I take them to okay. Also the canvas shells are set up like that too.
Alright, so, that's okay, that's important. So show that an odd plus an odd is even.
Okay.
Yeah, which is right.
You want to do this one?
Oh, I mean, it's just, that's what we should do.
So you got odd times even is even? Yes, yes, good. Try odd plus odd is even. Yeah. So, and you want to do this using modular arithmetic, which is actually a fair bit easier once you know how to do it.
Is it really? How would we do it with
So
modular?
this is good for an algebraic answer. So if you're working even odds with modular, think mod 2.
Yeah.
Okay, so what is an even number? What can you say about an even number mod 2?
It's 0.
Congruent to 0. And an odd number?
It's congruent to 1.
Congruent to 1. So if you take any even number times any odd number, what is that congruent to?
Wouldn't it be 1?
Well, what's your even number congruent to?
We have 2 times 1. Okay, it would be 0.
We have an n, which is our even number, and then n.
Well, we'd have a 2k and a 2k plus 1. 2k.
Or just n and m?
Well, n and n plus 1 implies they're consecutive. So would that really be thorough? As a
No, so I would do like 2j plus 1.
Or a different k.
Yeah, good.
And then mod 2, so the mod is 0.
Okay, so what's their product congruent to?
0.
Yep. And if something's congruent to 0, it's divisible by 2, so it's even. So that's all it takes. Alright, so use that approach, try to show an odd plus an odd is even.
You do like 3 integrals.
Plus 1, that's going to be 1. We're doing plus, so 1 plus 1 is 2, and 2 mod 2 is congruent to 0. And 4. Yeah, that is a lot easier.
The way he demonstrates, we have some odd integer, another odd integer. They would both be congruent to 1. We add up the addition of the congruency is congruent to 2, which mod 2 is congruent to 2.
That's what I would do.
So with the mod 2, you always have a remainder of 1.
Because they're odd. Yeah. I feel like you go into mod 2 is 0 if it's even, which feels like that would need a separate proof. To prove that mod 2 is integer if it's 0, proves that the number.
So mod 2 then is even. We already used direct reasoning to tell that mod 2 is even integers. And then
Put it as part of your proof.
Once like show you
can't just like show that. So it's like algebraic approach is a bit more straightforward. It doesn't require like the combining info and stuff that much. Nope.
Yeah. So I'm saying, think when you take it, period.
Yeah, I'll put like that off like 6 hours later for $16. It goes up in the end. It's like, I'm ready to
Yeah.
This will also be considered a 2 for the purposes of like multiplication. Yeah, like it's going to go to 2 or it's going to be negative.
Well, it was 2 minus 1, then you would end up with 2. Which we could run to 0.
I think in some cases it's better to consider it as a 2 instead of 0. Yesterday we were supposed to meet them. Can I get up my brother buyers? None of them want. Because like anytime you could just do all of them times 0. Either way, we can really do it.
Yeah.
So I'm like, I postponed. Let's do tomorrow. But I look at my pockets, I can't meet them. I'm like, oh my god, I can do it.
I love this class.
Somebody over. Yeah. Checks out the icons. All of them are dead. He
So
turns
you
them
can't
on.
turn them on to check them.
I also have a charger and you wait there for a day or 70 iPads.
Like every time somebody
Both
says
went up.
something in a state
It was like
line,
cooperative background school
but
district.
everyone.
So you can take the pictures. It's going around. It says, information allows public battleground to manage this iPad. So that is extremely sketchy. And so
Basically, we talk about the series and moving the iPad over and now.
could be he's a recycling company, so that makes sense where this
Yeah, that really.
Yeah.
instead it's very easy to take it out. Like, yeah, I don't want it.
No, yeah, you can transfer that.
Which is 2, which is
Because that was 70 iPads.
Yeah.
0, it must be.
Well, not only that, I don't even know if it's removable because it's a different kind of lock. It's the lock that only in school. That's just the way I have no idea. And even if you figure it out, there's still some trade-offs.
Yeah.
All right, and you got 1, 1, plus 1, 2, 0, even. Perfect. Good. All right, so I think everybody's got this. So let me throw you a parting question to work on for the next 5 to 10 minutes. So let's do a proof by contradiction. Let me see if this is true before I ask you to prove it. All right, so without using modular arithmetic, okay, using a regular proof from before we got into number theory, try to show that if the sum of 2 integers is odd, then at least one of those integers must be even. And try to do this as a proof by contradiction. So if the sum of 2 numbers is odd, one of the numbers must be even.
Even numbers.
Usually just to show the sum is
You were right then. Everything 1 plus 2.
Assume they're both
I was ready for
All right, excellent. That's the hardest part, is getting the negation correct. And you got it.
Okay. Okay, so we're showing that if n1 plus n2 is odd, then n1 or n2 is even. So we need to assume that n1 and n2 are odd, that one of them can't be even. And we need to show that by contradiction, that if they're both odd.
One of them is even, so now we're going to do proof by contradiction. Let's say neither of them.
negation, one is odd and one is even. The negation of that is still one is odd and one is even.
Yeah, we're doing proof by contradiction.
They have to both be. Okay, so we're saying n1 or n2 is even.
N1 or n2 is odd. Okay, yeah. So they both have to be.
If you negate n1 or n2,
Then it's odd.
it has to be odd.
So we prove, we try to prove that both are odd. And then we come to the contradiction that is one of them has to be even.
And then we're assuming that that's odd. So that the sum of those divide everything by 2.
We assume that the other two must be odd. And then, so, J plus K.
That's kind of, it doesn't say anything about the other numbers. What it actually said is if the sum of two numbers is odd, one number must be
This is
even.
impossible because this is going to be an integer and 2 times an integer is even. This is 2 times an integer plus 1. This is the definition of odd. This is the definition of even.
So how can you, so what's the hypothesis here?
It's supposed to be using
So back up before you do the I.
Without the modular.
Statement here, it's an if then, right? I didn't write the word then. If the sum of two inches is odd, I did write then, it must be even. So an if then statement, what's the hypothesis? Yeah, so it's the if part is the hypothesis. So the hypothesis is the sum of two integers is odd. The conclusion is one must be even. So if you're unsure how to start on this, try to write down the hypothesis and the conclusion of the original question, and then think about how do you negate the conclusion. And I'll chime in about 2 minutes.
Something like that.
So we just proved J plus K.
I guess we could say
Therefore, we have
the
contradiction. So they can't both be.
Yeah, it was
e and then integer.
They can't both be odd, so let's say they're both
is equal
even.
to
K plus 1.
Therefore, so
So we can say 2e equals 2e equals 2.
Therefore,
So by contradiction, n1 or n2 must be even.
Okay, so those three dots is the hypothesis for the conclusion. The implied thing that you're asking.
I was just an integer.
So to do an indirect proof, you want to start off by negating Q and then find a contradiction.
This contradiction, so are we saying that this is n plus n?
So we're saying this is true, because that's
You're right there.
and then we're going to say that
What?
But what we're really doing is a contradiction. We're trying to show C implies Q.
We're saying
That has a lot of problems at least.
At least.
She's probably not going to be very good looking, but at least she'll be smart and probably make a lot of money.
So let's say
I'm not way your thing at it.
Think about what does an identity take place. Written down with Q, so use the proposition with K or K, how you have negation of that proposition.
Just one is in the
Medium low.
Neither of them are even.
It depends how rich I am.
Q says at least one of them is even. Not Q says none of them are even. So what does that mean?
Who's about to go over it?
Not even.
look at it, call it go, and move and move.
Not Q.
or you can say
Oh, you're right.
which is a
Well, James are go odd, you just hit proof to show that someone is even. J plus K is even with your proposition. Q says some of those. It wasn't just starting with not Q, we found the contradiction. That's a really kind of tricky. But if you play around with it, throw some particular numbers in and explore that, I think it will help with this idea of indirect proof. All right, so we got a minute left, so let me chime in here. This is an if-then statement that we're asked to prove. If P, then Q. P is the hypothesis, Q is the conclusion. So the hypothesis is the sum of two integers is odd. The conclusion is one of those integers must be even. So to do an indirect proof, your first step is to negate the conclusion. So the conclusion is one of your numbers must be even. What's the negation of that?
They both must be
Neither of them can be even, or they both must be odd. So if we start by negating the hypothesis, we have the statement both numbers are odd. And now if you look at the sum of your two numbers, you just showed previously the sum of two odd numbers is even. But our hypothesis B says the sum of our two numbers is odd. That's your contradiction right there. So if you write down the conclusion, negate it, and then argue to a contradiction, you can assume the conclusion must have been true. That's the essence of an indirect proof. All right, good work. I will see you next time. Did you come in late?
Yeah.
Okay. We went through those on the video, so if you have questions about them, okay, cool.